So I hope you can see my screen now. So you should see
Yes.
one interferogram, right? Everyone can see it. Okay,
Yes.
perfectly. So the aim, the objective of the practical today is just try to generate by yourself this interferogram and then try to understand it a little bit. To do it, you have to install the Snap, which I already told you yesterday. So basically that you have the Snap, so and then to open it, so you have the data. I already sent you already the folder. So you can see in the folder you can have the data like stack data and stack here. Also, let I go back to the Snap. So I open Snap here, Snap here, right? And I open the practical system where it's here. So you should have the folder exactly like me. So we will go quite slow to because there is nothing to hurry. So everybody, you can you have something like a folder with allow you to appreciate where it's information, where the data is actually stored in your hard disk, and then to open it, you click on the stack here. So everyone follow me. So you click on this one and you click and you read and you wrap it here, wrap it here, and wrap it one here. So and then it will be reading. And then you can have this one in the Product Explorer. So very easy. So you can open the image and here, so you can appreciate what do we have. So we have one image and one image in 3 December 2003 and 11 February 2004. So we back a little bit for the interferogram here, just to explain you what exactly it is. So basically that there was an earthquake in Bam City in 26 December 2003. So basically that in 26 December 2003, there was an earthquake. So people want to understand what is the exactly happened in the Earth surface due to the earthquake. So to do that, people try to take one image before the earthquake. So in this case, we have something like 3 December 2003, and one image after the earthquake is something like 11 February 2004. So remember, the earthquake is in 26 December, and we take the image before and one image after to see the phenomena of the earthquake. So you have two images here. You can open it here. So you go, okay, you just double click on this one first, the first image, and the second image, you just double click on this one. So you already know that this is just an intensity. So basically, that's very similar to our human eye. So and you already know a little bit in the SAR introduction. So basically, that you can appreciate it by zooming a little bit here. So you can. So basically, that you can appreciate some information. For example, here is you have a structure like human-made, like here is the road and here is the city. So basically, the city is nearby here. Because why? Because the scatter or the target is very bright here. So very strong energy back to the sensor. So that's why it's kind of say very strong power here. The other one is not exactly the same because it's quite dark, and you see here darker because it's going to the rural. So basically, no one live here. Okay, here intensity, the first and the second. The first and the second is already do correlation already for you, but how can we be sure that it will be exactly the same position? It's difficult to appreciate if we just have a two folder like this one. So to synchronize the first and the second, so what we will do is we try to synchronize someone here. It should be a synchronized view. Okay, so we have a synchronized view. Okay, so whenever you have synchronized, you see it's automatically to help you appreciate the information because so we can zoom in a little bit more, and then we run it here. So here is second, and here is the first, and here is second. So you can appreciate the information. So we are sure that we did very well the correlation. So it means the two images are well superposed. So kind of say if we stay here, so like we zoom in here, so the target we are here. So here we have the target here. So 1, 2, 3, 4. So here is exactly 1 pixel. 1, 2, 3, 4. So here is the image. So we want to see is it changing or not in another image. So we go to here. So it's exactly the same. So you see here. So the superposition is very well. So we see exactly the same thing if we changing to from 1, 2, 3, 4 here. So it's exactly. So changing. You see? Any question? No?
No.
No, it's okay.
Okay.
For me, I have a small question. When we open the image, can you hear me?
Yes, very clear.
When we open the image with the snap, I'm not quite sure about the direction of the range or the azimuth. Can you explain it for me?
Okay.
I'm not sure. Yeah.
Very good question. How can we recognize which one is the azimuth and which one is the range direction? So yes, it's a quite a good question. So basically that one way is, so for the whole image it here, so here it's a little bit difficult, but so because if the whole image like this one is a little difficult, we a little bit more focused on a certain area, in particular in the mountain. If the image don't have the mountain structure, it will be a little bit difficult for us. Because why? Because if it is flat, so a little bit difficult for us to recognize where is the azimuth and where is the slant range direction. But it in azimuth, but it has the mountain, so you should see some structure like this one. So basically, what does it mean? If we have something like for shortening, I mean, the area here is already compressed a little bit here, and then behind this one, it quite a little bit dark. So basically, here we know very well that should be a mountain, and the mountain is here. So and the mountain is here. So let's check this one also. So this one is very clear for us to see where that is exactly the mountain here. So basically, you have something like layover or for certain it happened here, and behind this one is kind of say layover. So from that point of view, you will see very easy the direction where we look to the ground. So basically, the satellite on the top here, and they look back, look in here. So they look this one, and they see this one's very strong because the top of the mountain is going back to the sensor first, and then to the ground. So that's why they have a very strong power here. And then behind the mountain, there is very dark because the signal cannot go back behind, of course. So, and then you can see here, so from point of view from here to here, we recognize, okay, this one should be in horizontal here, should be exactly in the slant line direction. And then the vertical should be in azimuth direction. So just try to a little bit repeat that. It's very easy when we have the structure like the mountain, because in that case you can see where the shadow, where the line over for sorting it easily. But with no mountain structure like this one, so this one is we completely lost. We don't know which one is the azimuth and which one is the rain direction, right? You follow my comment, my explanation, everyone?
Yes. I'm quite sure about that. Thank you.
So, okay. So basically, that we already tried. We be sure that in vertical it should be azimuth, and in horizontal in slant line. Okay, so but basically that in the SAR data, usually if we open from the raw data, usually in the not 100% correctly, but usually in the vertical it's azimuth direction. Why? Because in azimuth direction, they stop in here, they collect the image for the whole column here, and then they go and get the whole image in the column, and then they go get the whole image for the column. So that's why usually for the image storing of the SAR acquisition is naturally the azimuth direction is along the vertical. So, and because why? Because at each position they can recall one line, and each position they recall one line, and so on. So it's naturally to record the data like this one, but it's not 100% correct. Because why? Because the developer of the software, they are freely to go vertical or horizontal. It depends on the developer also. So if they define the format azimuth in the horizontal, they are freely to do that. But usually people prefer azimuth in the vertical direction. If we don't have any information, we can based on the structure, based on the target, based on the interpretation that we already done. So we know very well this one is azimuth. Okay. So just want to repeat it a little bit again, because it's important to understand the concept of the superposition. So you see here. So basically here we have that's in the first image. So you have a very strong scatter here. And then going to the second image, you have even more strong structure here. What does it mean? It's changing a little bit here, but the time is not really a loss. So basically we have pre-December until February. So basically 2 months and less than 2 months and a half. And less than 2 months and a half, it can say it's just 70 days. And you see everything almost changed. So it doesn't change a lot, but it's changing. So in that case, usually that people have to end up with some decorrelation, like we already know that should be related to spatial decorrelation and temporal decorrelation. But from here to here in the image, so we see very clear that due to 70 days later, the first image we have it here, and the second image we have it here. So kind of say there's just one target with somehow stable, somehow unchanged, but the other one is changed a lot. So you see here, like this one, we just have one strong power here, one strong target here. But going to the second image, we have many strong targets here. So basically, if we go into many images, we can identify this one easily. And for the technique lab, like we already, I already told you yesterday that if we select some stable target, and this one should be very good candidate. Why? Because the first and the second, it is still there, and the other one is not really a good candidate to select a stable target. So you know the meaning of the stable target and why it's changing because of the temperature, because of the time, everything can be changed. That is nature. So we are sure that two images is very well superposed. And then what do we do now? So we have the first image, the second image, and they are well correlation. So we're going to generate interferogram easily. So basically we're going to the menu of the snap is here. So we're going to the radar, we're going to interferometry, and then we're going to radars. And basically there's a lot of products we can calculate easily. So basically that we can select interferogram formations. So you click on this one. And then we select the data. So you already familiar with Snap, but maybe have you ever tried Snap after my class, or is there any class who also using Snap software?
Yes, Mr. Bing.
With Ben, he's also using Snap. Okay, so because Snap is very powerful graphic user interface software. It's fast and it's free, and that's the key thing to appreciate that. So basically, that's you have the data. So you put this one here, so that we don't have anything. We just have one here. So put this one here, and then some for the directory of the album. So basically, I don't want it here, so I want to put it in where we can appreciate the information. So basically, you should put where is this basically document. We're going to city. I'm going to do answer here. We don't okay. We want to have a little bit okay. Bam. Okay. Processing. Okay. So we put this one. We select this one. So we put the folder. So remember the folder. It should be you can put anywhere you like, but you should remember where it is to retrieve information when needed. So the processing parameter. So the processing parameter. So where we are here, we want to put we want to subtract it the the flattening phase. So basically that you already know that when we subtract the phase information, you have to estimate the flattening phase and subtract it. Here they offer it directly here. So we subtract this one. We select on this one. We select subtract. So basically that they explore information from the orbit and then we calculate this one. And then the other one we keep it the same. So we just run it. So just want to repeat it for you because maybe radar, interferometric products, interferogram formation. So we take the data, we take to the this one. So we take to it. So processing. So remember, okay, so we got this one, you got this one, and you just hit a run. So basically that when we calculate the two images, we subtract it and we also estimate the flat Earth phase, so basically the flood phase information, and we subtract it from the original phase. So the data we have, it should have the phase with it very clean. Okay, so you can appreciate that information by using this one. So you have the information of the complex data. They start to band to component, and then intensity, and then the phase, and then coherence. So basically, you open the phase, so you see it here. So that is the phase which we already subtract the flood phase. So you can open it here. You see here, you can appreciate some fringe. Very easy, because why? Because it's quite clean and it's quite beautiful. But what I just want to be sure that without the flood phase, how's going on? Suppose that if we can recalculate this one again, but this one is not not subtract flood phase. So basically no flattening. So it means that we take this one, we generate, but we don't subtract the flood phase. So you follow the idea. So we don't subtract the flood phase. So basically that you have no flattening. Okay, so we run it to see if there anything different. So to appreciate why we have to remove the flood phase. So in your opinion, what will it look like? So everyone, in your opinion, what will it look like? Can you try it? Can you try it before I open it? So in your opinions, what will be different between this one and this one? In my opinion, I expect that this one should be very rapidly changing at the phase. Basically, it should, because that include one phase ramping. So let me check it. Is this correctly? So you see here. So this one is already subtract for the flood phase, and this one is include for the original phase. So basically, you see here, there's a little bit of the linear ramp of the phase. They go into a little bit quite linear here, and that's why people can easily to estimate. So you see the difference here. So here is the one we already subtract for the flattening phase, and here is the one before. So basically that if we don't know anything with the SAR interferometry, it's okay. We take the first image and we subtract the second image, and we got this one. So, and this one is already beautiful. So if we know a little bit more, we can subtract it, the flattening phase, and we got this one. So, okay, so the idea with the flattening is to try to remove the not necessary of the fringe. So basically that the number of fringe here is much more less than the one in the flattening. So we have the phase, and we can appreciate the information like we already yesterday. We know that one metric appreciate the information of the phase is the coherence. So basically this one they estimate for you the coherence also. So basically that's if you click on the coherence, what we are expect that it should have a one image which contain the value vary from 0 to 1. And then what I just want to show you here for same model, like this one. So we see the information is very clean here. So basically that the signal is very good here, but it's quite crazy here. Basically it's just noise and we don't appreciate anything. And then if we go far away here, you see here there is some maybe some phenomena of the Earth surface here. Maybe the surface is corrupt here a little bit. So that is why you see just a little bit noise along this line. So we can expect that the coherence along here should be close to 0, and the coherence, this one here in this area here should be very high. So is it correcting? So you see here. So you see this line. We show you very noisy phase, and when we go into the coherent, and the bright one, it means it's close to 1, and the black one, it means it's close to 0. So you see very clear that the signature of the coherent showing us very well that it's very dark along the line here. So exactly in the phase. But with the phase, we don't. We just had the phase. We don't know the quality, and the coherent is a good one to know the quality. How can we be sure we talk the same thing? We can extract the information to appreciate it a little bit. So how can we extract information? Just have a look a little bit. So basically that we're going to the cross profile here. So we click on this one. Okay, when we go cross profile, click on this one. So you see here. So if we starting from here to here, that's the coherent. If we go into something like the coherent, is going to something like from 0.8 to and then they going down to about 0.1 here. So basically here is 0.1, and here the back again about 0.8, 0.9. So the coherence of the phase around this area is very high, very good quality for the phase, and for coherence here it's terrible because basically that's just 0.1, and 0.1 is practically we cannot use any information from the phase. And it's true because here the phase is crazy, so we don't see anything here. So that just to confirm you that coherence is a very good metric, very good index, very good indicator for you to appreciate the phase quality. So okay, so let me just remove this one because it's not necessary. Okay, so what we do next? So basically that's we can appreciate some information like coherence and the phase, and we can appreciate the flattening phase. And then what do we need to appreciate? So basically that before we moving on, we just try to understand a little bit more about this image. So basically that you see here. So you see the image here, some kind of appreciate, but not really in a good way. Because why? Because it's kind of say it's kind of very tall image. It's not really square, and with the human eye, when something is not really square, is a little bit difficult to appreciate. So what we want is we want to try to make this one a similar ratio to appreciate the information. So if we want to do that, we have to check carefully what exactly in the column resolution. Basically, what is the size of the pixel here. So if we go very high here, so what exactly the size here? So here is 1 pixel, so they have 1 value. But what exactly the size from here to here is how much, from here to here is how much. So to do that, we can appreciate that in the information. So basically, that's in the metadata. We track in the abstract metadata. I think is correct one. So you can open the abstract metadata, and we can appreciate the information that we have here. Something like, okay, so we have the azimuth range and azimuth spacing, range spacing. So basically that's the size, the type of the pixel in range direction and in azimuth direction. So let's check the, so basically that the range direction is something close to a meter, and the azimuth direction is close to something like 4 meters. So this image is what kind of image? This one, this image is about the ASAR, the ASAR image. The ASAR image, it means it's collected by the mission, what we call the Envisat. So basically that's the mission of the ESA, European Space Agency, with a long time ago, which is something like 20 years ago. And it's already dead in 2010. So basically that this is old data, because this is 2003 and 2004 is very old data. And with the old data, so basically this one is strip map mode, because in the past there is no top mode like nowadays. And with the strip map mode, we usually that the azimuth direction or the azimuth spacing is very high, very good with respect to the range resolution. So remember, for the strip map of the ASAR data, you can see here the range resolution is something like close to a meter, and the azimuth stay equal to 4 meters. And in the contrast with the modern data like Sentinel-1 data, the range resolution, the spacing in the range direction is very good with respect to the azimuth spacing, azimuth direction. And the question is why? For example, with the Sentinel-1 data, the range resolution on the range spacing is something like 4 meters or 3 meters, something like 4 meters. But for the azimuth direction with the Sentinel-1 is something like 20 meters. And could you tell me why? Maybe you don't have such information, but I can open one image just to help you understand a little bit more about the Sentinel-1 data. Okay, I can open one image. So basically that I should have one here. So basically that's the image I have it here should be this one. Okay, like this one. I have one image from Sentinel-1 data. I open one image here. So okay, so I have this one is from Sentinel-1B. So what do I want? I want to be sure that the range spacing and the azimuth spacing of the ASAR sensor. So basically that the image from the script map of the Envisat mission with respect to the Sentinel-1 data. So Sentinel-1 data, I open this one, I open abstract metadata. So this one is for the script map, and this one for top, and I expect that the range spacing, azimuth spacing. So you see here, everyone. So I put it here for you to appreciate that information. So for the script map and for the so here in the script map from the ASAR product of the Envisat mission. So a range spacing is something close to a meter, and azimuth spacing equal to 4 meters. And for the top of the data of the Sentinel-1 data, range spacing is something like 2.3 or perhaps say 2.5 meter, and azimuth direction is something like 40 meter. So why the azimuth? My question is why the azimuth in the topmost in the Sentinel-1 data is much more lower with respect to the range direction? Follow my question, everyone?
Yes. Is it because
Yes.
it's top small then, so it has less time to scan on the azimuth direction?
Exactly. That's a very good answer. Because why? Because azimuth azimuth resolution, it depends on the aperture, depend on the synthesis aperture. I mean the duration in azimuth direction to collect the data. With the strip map, they exploit all the time in the aperture time to collect all the data need. For the top, they during that time exactly the same like strip map, but they have to do many observations in many different angles. So that is why at a certain angle, they don't have enough time to make a synthesis aperture time to do very good azimuth resolution. So basically with the topmost, we have very good coverage, bigger image, but we don't have a good quality wood resolution in azimuth direction. Because why? Because we don't have enough time to do synthesis aperture like the strip map. And that's why you can appreciate that the range in the past, they don't have a good quality with respect to azimuth, because azimuth in the past they have plenty of time to do focusing. For the topmost, the azimuth direction is very poor quality with respect to the range. Because why? Because they during the same time they have to do a lot of job, and then they don't have enough time to have a good data to do focusing. So basically that they work very hard, but they have to pay for the cost of this azimuth direction. So this one is quite important for you to explain to remember. Because why? Because in some time when we do processing, we need to understand what exactly the resolution here to put exactly the parameter we need. So basically, when we do the parameter we need, we exploit a certain window with appreciate in a square dimension. So basically, if we're talking about the topmost, if we take azimuth in 3 is mean something like 40 multiplied by 3 is something like 45 meter. And 45 meter which we be respecting range is something like 20. Something like 20. So basically, if we take a square window like this one, like if we take the square window like this one, so basically that we take in range direction we take 20, but in azimuth direction we take something like 3. So that is why we can end up with a certain window like 3 multiplied by 19 or 3 multiplied by 21. And why it does? Because of the resolution is different between two directions. And that's important for the SAR data, because with all the data like optical image, usually they have exactly the same dimension in the vertical and in the horizontal resolution. With the SAR data, the resolution is completely different between azimuth and the range direction. So that is the Sentinel-1 data to appreciate the difference between the azimuth and the range. So I close the progress here. So we're back again here. So CAP say the range resolution is some kind of a double time. So they have the double better quality with respect to azimuth. So okay, so and then we want to check more information. How about the number of row here and the number of column here. So number of for the image, what about the number of column and number of row here? So where is the dimension of the image? So where is this? So it should be, so you see here, so we have something like 3,000 number of column here and 15,000 number of line. So basically that's a from here to here is kind of 5 times. So that's why you see number of line is 50,000. So and the number of line is exactly corresponding to azimuth. So one way to appreciate the quality if we want to improve it by the multi-looking. So multi-looking is a technique that we exploit a certain window, and then we take the average inside that window, and we substitute all the element inside window by just one value. That is a multi-looking operator. So basically, we want to improve this product based on a certain multi-looking operator. How can we do that? We do just kind of say radar. We go into where is it? We go into utilities. So basically, that's some useful information, useful library to calculate for this data is multi-looking. So when we go multi-looking, then we ask you, okay, what is the information you want to input? So you take the interferogram with already subtract for the phase flattening and the processing output. So you keep it here. So you want, you want to have the square pixel, or you want to have independent upload. Suppose if I want to have independent upload, I can get range and azimuth. So now the information, now the knowledge of the range spacing and azimuth spacing is very good for us now. So we know very well that the range spacing in this image is some kind of close to 8 meters, and azimuth is something like 4 meters. So if we want to put something like, okay, like 2, like number of look like 3, if we want in range 3 we multiply by 8 something like 24 meters, and here is something like 4, and we want to multiply with 5. So we can adapt it a little bit more. So basically we can put a 7. So the number here we can do it based on the knowledge of spacing. So basically I want to put 3 and 7, or even I put another line is okay, no problem. So it's okay, so everyone. So the way we put it here is just to appreciate the spacing, and the multiply up 3 multiplied by 9, we end up something like 27 samples, but it's not really 100% independent of the 27 sample. Because why? Because this can be very high correlated between the pixel, between the samples. So suppose that I put 3 and 9 here. So and then we just hit the run. So we put here the multi-look, we run it. So it's very fast with the snap. So basically that from here to here, I can appreciate the information that is the face here. So you see here, and we see some kind of, it's not really square. So we don't want this one because it's not really beautiful. So we want a little bit more square. So we want more, maybe want more. So we can put something like, okay, we want more. So we want to put here. We want to put here like something like square. So we can put something like, okay, we put square here, and if we put the 3 here, like so, okay, some people can put this one 3 by 3, and then we can run again. So basically that's we sometimes we do we ad hoc processing. So ad hoc processing. So basically, we learning. So you see, this one might be more beautiful, but what does? It's constraint for us to see this one. The constraint for me also. Maybe there's something wrong with the processing. Let me track it. So basically, that we remove this one. We want to calculate this again.
My image doesn't have that.
Sorry, Thao. Yes.
Yeah, my image, my result doesn't have that part. So I
Okay.
think your snap has the problem.
So that's why it's strange for me because this is the first time I saw this one. So let me check it correctly. Why? All right. Okay. All right. So it's little bit strange. We see. Oh no. Okay. So you see here. Just do it again, and the alias or the error can be gone. So maybe just so we end up with this solution. So basically, that we don't want this one. We don't want this one. We can remove this one. We don't want this one. We can remove this one. So we have this one. So we have the multi-looking product now. And with respect to this one, which one is more beautiful, everyone? This one, the one we do multi-looking is much more easier to understand, easier to appreciate, easier to do certain interpretation, something like that one. So even from now, we can do some interpretation like we done sometime with this interferogram. Is there anyone who want to help me to show with everyone that what does it mean of this interferogram? Before we doing that, I just want to ask you: did you finish with your software and then able to produce the image like the one I show you? Everyone?
Yes.
Okay. So, and then I need one person who volunteer who want to just to try to explain it. What does it mean, this interferogram, and what is exactly information inside, and how can we appreciate that one?
Well, I guess
you wait. If you want to volunteer, can you just share your screen? I just Maxim, you want to explain this interferogram for everyone? You want it?
Yeah, I can try.
Okay. Okay, I can make you. Can you share your screen and try to explain everyone what it is, this interferogram? I hope until now you can understand, you can appreciate that. Okay. Yes. Okay. Very nice. So you are able to do exactly the same thing. So feel free to explain it, what it is and how can we appreciate the information. Perhaps say how can we quantify the information.
Well, we see these fringes that are like circular around this point and this point. So I guess the land has probably sunk inside. But I don't really know how to interpret if it's higher or lower. So I guess this might be because with the fringes, maybe since it's going to I'm not sure about the sign of the elevation, if it's positive or negative, but I guess with earthquake, it's probably negative and sinking. And to quantify, maybe we can draw a profile like this, and we could count the fringes. And by counting the fringes, we could know the how many meters it has sunk by knowing what the baseline and the fringe correspond to for this satellite and for this processing. And then we can know that it's like 1, 2, 3, or we can do it maybe with by going just to the center and drawing.
Yeah, it's better. Yeah.
And so we would, it's 1, 2, 3, 4, 5, 6, 7, I guess, fringes. And if it's 10 meters, then it has sunk 70 meters from here to here. And we see that here the topography is changing much more rapidly than here, because the number of pixels between the two maximum of fringes is higher than between this one and this one and this one and this one. And yeah, I guess this must be all.
Yeah, it's beautiful, Maxim. Thank you. Thank you a lot. Yeah.
Thank you.
Yeah, it's very nice. So yeah, you're right, totally, Maxim. Basically, that we can appreciate the information of this interferogram by counting the number of frames, and basically that we know very well that the earthquake is here because that everything Detroit was Detroit here, so we know the center is here. So it means that if we go a little bit far away, the effect of the earthquake will be very low impact. So basically, we assume before the earthquake and after the earthquake, everything is stable here, so nothing changed. So if we counting the number of frames from here to here, and we can appreciate the quantitative way the amplitude of the earthquake, the amplitude of the displacement here. So if we go from here to here, we can easily count how many number of frames. So for example, if we started from the blue one here, so blue one here, blue 1, 2, 3, 4, 5, 6. So basically 7. So 6 or 7 number of frames, and we know very well that one frame here is corresponding to how many of the displacement, how many of the displacement here. So he is not the topography changing, because why? Because we already removed the no. Do we remove the topography contribution, everyone?
Yes.
Let me check. Unfortunately, no. But because why? Because we can appreciate the information of that of this one. Why we can appreciate the information of this one? Because why? Because the baseline here, I remember, is very small. Basically, that 5 meters. It means that the contribution of topography is almost close to 0 in this interferogram. So that's why the whole information of the phase here is correctly represent the displacement. So basically, if we count the number of frames and we multiply the amplitude which corresponding to the frame, and each frame here will be corresponding to how many millimeter. So as I already told you that he is the ASAR Envisat data, and it is some kind of what is the frequency. Frequency is something like this one. Is 5.3 gigahertz. It corresponds to exactly the C band. So the C band where the wavelength is something like 56 centimeter. 56 millimeter. So basically that one frame from here to here is corresponding to exactly half of wavelength. Kind of say from here to here, the displacement of the surface is changing something like 28 millimeter. So by counting number of frames, 1, 2, 3, 4, 5, 6, 7, we multiply by 28, so we end up something like 17 centimeter, and we should know which side is, and to tell us from here to here it really going up or going down. So basically we know very well here is close to 0, and here is something like 17 centimeter. It's going up, it's going down, we don't know. Because why? Because it depends on how we select the image. We can take the first image, subtract to the second image, or we can take the second image, subtract to the first image. So suppose that from here to here, the phase is changing how much? So basically that, let me track together with you. So basically from, we see here, well, to present information, we have to understand the color pattern here. So basically the color pattern here. So the color pattern you see here, the color pattern is starting from the violet one. So the violet is going to the green one, the violet is going to the green one, and going to the blue one. So violet, the green one, and a blue one. So basically from here to here, the phase pattern telling us that the phase is increasing. So the phase is increasing. So basically that if we assume that in this case the phase is increasing, it means that the distance between the sensor and the target is increasing. So basically if the distance is increasing, it means that this one is going down, because why? Because the distance between the sensor and the target is go a little bit far away. It means this one is going down here. So from here to here is going down 28 millimeter. From here to here is going down 28 millimeter. From here to here is the total number of 7 frames here, about 70 centimeter. And then the interesting thing is if we go all the pattern here. Like if we started from here, so basically we started from the blue one here, and it's going to the green one, and it going to the violet one, and it going to the blue one, and it's going to the green one. So you see here the pattern from here going to the center is quite a little bit different. So basically they started from the blue one and they go to the green one. So the blue one, or the green one, the blue, the green, and the violet one, the blue, the green, and the violet one. It means that from here going to here, so from here to here, 1 frame, 2 frame, but the frame here is a little bit kind of say decreasing. So you see the different pattern here. From here to here, the phase is increasing, and from here to here, the phase is decreasing. So basically that if we assume this one is going down, so this one from here to here, they very clear going up. So from here to here, going up about something like 28 millimeter, and we can count number of frames here. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, or 11. So basically from here, we go to the top here, 11. We can appreciate that information by just click one. Let me track this one. So if we click on profile, so we can appreciate the information. So how many number of frames if we count in here is must be more easier. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, something going to 11 here, 10 or 11. So basically that it will be, and you see the phase is decreasing. The phase is decreasing. It means that the pattern from here going to here is totally different from here going to here. So this one is going up, and this one is going down, and this one is going in up. About the amplitude of about 10 or 11 number of frames. So basically that's about 28 centimeter or 31 centimeter. So we do nothing, we just based on the image, and we based on our knowledge of the 1 frame corresponding to the half of wavelength, and we can quantify how's going on with the phenomena. with the interferogram, with the earthquake. Do you agree with me, everyone? You follow?
Yes.
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 Okay, so I hope that you can follow everything. So, but to be sure that everything correctly, we want to estimate the topography estimation. But before doing that, I just want to talk with you how can we find the baseline information if they can have available. So basically that you see here. So if we open in this one, we can see the baseline information. Here we click the baseline information. So basically that we have this one, show temporal baseline, we track this one. So you see here, the baseline here, you see, everyone see my baseline? So it's telling us that the baseline here is very, very close to 0. So it means that the baseline, the geometry contribution, I mean the baseline sensitivity to the topography is extremely non-sensitivity at all. Because why? Because with the 0 baseline, we don't see anything with respect to the topography changing. And you can see that for the high ambiguity here. So this one telling us that if the phase is changing something like 2 pi, is corresponding to something like 14,000 meter changing. Everybody follow this value? It's telling us that if the phase is changing 2 pi, I mean 360 degrees, and the topography should change in corresponding to something like 40,000 meter. So in that case, the phase is telling us that the topography here is very minor impact to the interferogram. Even the average how tall it is, it never touched to the 40,000. So basically that for the BAM city, the mountain is something like a few hundred meters. So it is safe for us to ignore the baseline, the topography calculation and remove it from the phase. But in that, if we need, it's quite easy also. Because why? Because if we done interferogram here, we go to radar, we go to interferometric, we go to borders, and we can estimate the topography phase removal here. I just want to calculate it and then to show you is it changing or not our parameters. So basically that we subtract the atmospheres. So okay, we want to understand it. So we want to understand the elevation. We've done it. We run it here. For the topographic phase and removal, it's a little bit slow. Why? Because they have to find out where the digital elevation model available, and then download to your computer, and then they use that information to estimate the phase. So basically, they estimate the topographic phase, and then whenever they done it, they subtract it from the original phase. So that's why it take a little bit longer rather than fast to understand. So basically that's where we are here. So tactile a little bit. quite slow. So we're doing, but I'm sure I expect that the result it should be exactly the same. Why? Because the topography, as we already mentioned, that the baseline is very small, so the topography contribution is very minor. So subtract it or not subtract it, it's not really changing the interferogram. So, but let's try to see. Is it done in your computer?
It's also running.
Okay.
Not yet.
Okay. It's constrained that it takes so long to download the data. I expect that it should be faster. It's constrained for me because it takes so long. I'm not sure if you have done it. Is there anyone who already done it for the topographic phase removal?
Yeah, I completed. But unlike you, I ticked all the boxes for the output topographic phase band and yeah, the last one, long band.
Yeah, it's a bit.
Me too.
Let me try to figure out what happened because for me it's too long. It should cost something like 1 or 2 minutes maximum. Here it's quite 4 minutes already. Let me check. How can we do it? How can we handle this one? Why it takes so long?
Did your Snap download all the necessary components to write?
Oh, I think so. I just installed the very latest one of the Snap this morning, so I hope it will be fine.
Because when I did mine, it started downloading stuff in order to make this
yeah, okay.
procedure.
So in my computer, they don't have anything. So let me check if there's something wrong with Snap. I try to cancel it and then try to maybe there's something wrong with no, even I cannot stop it here. So let me try it another way. This one might be better. So snap it here. That's true. Good job. Okay, so I'm going to snap it up here. So to be sure everything is perfectly, I just want to check that what happened. So let me see if there anything for update, something like this one. Maybe there's something wrong with the cloud computer. Let me check. Let me try to update it a little bit to be sure nothing wrong. So it's strange for me.
I got some results in like.
You got it?
Well, it took only 10 seconds, not even. So I'm not sure it's correct, but let me show you because I didn't save the result in my memory. But let me show you.
Yeah.
Can I show you?
Okay, so massive.
That's it.
Go ahead. Yes. So can you open the face?
Okay.
Yes, the face.
It takes a long time, but.
Why just a half of the image? Can you click on the why the image is the whole but the face is just a half? No, because it's kind of a bit slow, right? The intensity, no. Can you click on the?
It was working 1 second ago.
It's kind of freezing.
Yeah.
Maxim, for the snap, whenever it fade with the freezing like this one, the best way is just try to stop it and open it again. That's the best way.
But I didn't. This is because the computation took not too much time. But I think it's because the files created are really low, really large.
Yeah.
And because
it's unexpected. What's the terminal? Okay, let me go back to my screen to see how's going on with the snap. It's the downloading plugin. Okay. Oh là là sao? Oh là là sao? Sample pizza. Strange. So maybe we can take 10 minutes to take a break to download the data or something like that one. We get back in 10 minutes. Everyone, okay?
Yes, okay, thanks.
Okay.
Okay,
Yes.
it's okay.
Okay, welcome back. So I just try to restart the Snap after the check for updates. So I hope everything will be fine. So
I also
just to be yes, I listen.
Yeah, I also restarted Snap, and the results I got before are good.
Okay, very nice. So I hope I can follow you immediately. So let me check. So we have the interferogram. So basically that this one. Okay, so we want to estimate the topography and remove it. So we go to radar. We go into interferometry and we go into the topographic phase removal. So, and then we have this one. So we have this one. So we want to estimate the topographic phase and the elevation. Okay, so interference. I hope everything will be fine because after the check of that, so it should be fine. Yeah, it's running. So my guess it might be there is something wrong in the server where store the DEM. Basically, the SRTM information is changing, so they update for the link on the server, and it's we find out. So you see now it's about few seconds. So basically, that's why when I saw it's a couple of minutes, it will be strange for me. So let's check together. So basically, that is the one we have the topography phase. We subtract. So you see here. So basically here is before the topography and it's after the topography. You see here. So the topography they contribute something, but not you see like this one. This one is before topography and this one is after topography phase. So basically that they are a little bit changing, but not a lot. So let's check the topography phase. So if you see here, it's quite very smooth. Let's check the ramp. Okay, let me check. So you see that the phase of topography is very smooth and very small. And if we consider if 2.5 here is very a small contribution. So, but basically that we estimate it and we remove it from the interferogram, it will be better. So basically that we stick with the one we remove. So basically that we subtract the reference DM. So with this one, and we moving on with the this one to do multi-looking. So basically we select this one and going to move multi-looking. So we do this again and with the like a tree here. So we going to run it. So and it's really nice. So okay, so that should be the one we are expecting because why it's not changing a lot and also it's very nice interferogram. So so you see here from just based on the one here, the previous one here. So this one is before we do multi-looking and we see the information from the interferogram. It kind of say it's a little bit, it's beautiful, but a little bit noisy here because why you see it's a little bit noisy here. But if we go into multi-looking, they exploit the window and estimate the average, and you see the information is very nice here. So it's still a little bit noisy, but it's very clean. You see here. Okay, so I hope everybody can can repeat my processing easily after do something like I did, like just check for update, like going to have and just check for updates. Sometimes we need to check for updates of the snap, otherwise they will be end up with some unexpected freezing. Okay, what will we do now? So let me check in the lecture. So basically that we had this one, Topography removal. We got this one, we're multi-looking. 2 or 20s. Okay, we got this one. So now what do we have here? We can even reduce a little bit more by filtering, something like, okay, constant, something like going to interferometric, going to filtering, going to constant phase filtering. We can do this and we can improve it a little bit more. And even we can do everything from the beginning just by using just one graph like this one. So I suppose I will try to do again everything, but with the constant filtering. Okay, so I'm going to the constant filtering, and then we're trying to repeat it here. So we're going to radar, we're going to interfere, we're going to filtering, and going to this one. So we have this one. So basically that we keep the same the default parameter in this quantify. So we got this one. So you see the phase is from here to here is the phase is a little bit better, like this one you see here. You see, like this area here, you see, from here to here, the filtering they require smart enough to know here it should be clean, and they try to remove some noise, and not like this one they recognize it's kind of say noise here, and they can improve the information. So very nice filtering. Okay, so what will we do now, everyone? So basically that we have a very nice interferogram, very clean interferogram now, and we want to do something like fan wrapping. Why fan wrapping? Because you can see here, we see. So here is the phase information. So basically that what you see is the phase is changing from about close to 0 until about 3 radians. So basically that's 3.14, and then they rapidly decrease to minus 3.14. Why? Because that the way people store the complex data is just in one value, and they are not able to store the absolute value of the phase. So that's why when they take the term of the imaginary and the real part of the complex number, they got the angle, and the angle will be automatically wrapped into the minus 3.14 and plus 3.14. So that's why you see here the phase is always wrapped inside here. So what we want to do is we want to unwrap this one. So basically it started from here. So we expect that something should be continuously like this one. So basically that we want to change the color here. So basically from minus 3.14 until 3.14 about absolute value. So basically it should be something like this one. So we want from here to here. So to do that, we have to do some kind of what we call already phase unwrapping. So what does it mean phase unwrapping? Basically that they just try to retrieve the absolute phase, like this one, like from 0 to 26 radian here. How can we do that? We just in Snap it's a little bit complicated to do phase unwrapping. Because why? Because Snap they don't have the built-in function to do that processing. They have to exploit the other software, the third-party software, what we call Snafu. So basically, they have to try. What they are going to do is we try to have the data, we export it into the Snafu, we do fair wrapping, and then we import to the Snap system again. So it can say a little bit complicated. So how it's working is we are to fair wrapping, we export the data, we set it to 1, we set the model to information, and we got this one, we got Snafu, and we got this one, we can run it in the terminal, and whenever we got terminal, we are going to import here. We take this one, we select this one, and then we going to done it here, and we can see in the script. So let's do it together. So basically, that we have this one. Okay. Just before I'm moving on, everyone is where I am now.
Yes.
Could you quickly just show how to do the filtering again?
Okay, very easy. You're going to radar, you're going to interferometric, you're going to filtering, you're going to constant phase filtering. Okay.
Yes.
And then just select the products that we already done for the multi-looking. And then we're going to processing. We get let it be, and then we just hit the run. And then it will be done. Yeah. So I suppose that everyone is where we are now, where I am now. So what we are going to do, we try to do fair wrapping for the whole image here. So we're going to radar, we're going to interferometry. So everything is in this menu. We're going to fair wrapping. We're going to Snafu export and do it this one. So before I'm doing this one, I just want to check with you that you should install the Snafu. So you're going to the many tools together. So everybody a little bit pay attention here. You need to be sure that you have that Snafu. So you want to plug in, and you should have this one available. So basically that install. So you should have this one Snafu fair wrapping. Do you have this one installed? If no, is okay. You have to go into available plugin, and you select the Snafu fair wrapping here. For me, I done it already, so I have this one. So before we moving on, please install the one that I just mentioned, the Snafu Unwrapping. Okay, everyone?
Yes.
Okay. You happy?
I just installed it.
Okay. When you install it, you have to kind of say restart the Snap to make the system understand. So kind of say just refresh the system. So you install it and you restart the Snap, and it should be available here. And whenever you done it, we go moving on. We're moving on by going to radar. So going to interferometry, going to fair wrapping, going to Snafu export. So we got this one. So basically that's the products that we want to export is the one we do subtract for the topography, do multi-looking and filtering. So we want to export it where, so it should be the one where we do processing here. So basically here. Okay, so we put it here. We look at Snafu. Okay, and to be sure that the number of rows and column here, usually that the Snafu they offer the time processing. Basically, if the image is very large, though they can divide the image in many bars, small bars to do processing efficient. But sometimes that it will be end up with some kind of jumping between batching, and it's not really good. So we try to put this one equal to one. That's enough. Because why? Because our data is quite small also, so it's not really necessary to do many row and column, just select one and one. So this one and this one. So everybody follow my instruction?
Yes.
It's okay, Bảo Anh? You follow my lecture from last 3 days? So okay, no problem. So basically that.
Where can we find the Snafu Snafu folder?
Here you can this one. You go to your processing chains. You copy this one. You put it here, and you
okay, we just have to,
Snafu.
Okay. Thank you.
Okay. So everybody follow. So the important thing is should be one here. Should be one here. Everyone, it should be one here and one here. Like I should mention it in the how can I say in the this one. You see here, I highlight it a little bit here. Why? Because it's important, yeah. Okay, whenever we done it, we just hit the run and hope everything will be fine. Okay, so it's very fast, so it's done. So basically, let me check the Snafu. So you see here, they have this one. So you see, they usually that they will try to export the coherence, because the coherence is very good data to help us to understand the quality of the phase, and then it will help us to understand how to do phase unwrapping correctly. And then the Snafu configuration here. So basically that you can open it here. So if you don't know how to do it, you can do it in the terminal or something like this one using this command to call Snafu. Let me try to do together in the graphic user interface. I hope this will be working. So yeah, go to radar, go into interferometric, go into interfero, go into phase unwrapping, go into Snafu unwrapping. Click on that one. So let me check, is this correctly? So where we are, we go to this one. 50, go into this one, go to minus, Snafu, and this one. Number 4 is correctly. So let's track the output. So let's track the output here. Okay, so the parameter, let me track everything fine. If not fine, we run it. Correct, but Snafu. So they ask. Okay. Just run it again. They don't show up anything. Let me check if you done something. No, they don't show up anything. Let me check. I always have problem with the graphic user interface. Why it's so difficult to get?
I have the same problem.
Okay, don't worry. I have the solution, but let me try the graphic user interface. Because why? Because it's easy for us if we do like this one all the way. We can end up with this. So we want the face. We click on this one. Okay. And we run it again. So just I run it and have, okay, it will be run, it's running. So basically that's correct one. Because why? Because we need to carefully with the input parameter. So basically it's running here. So 27 parameter input from Snafu. Okay, it's running. So improving. It will be finished soon because Snafu is very fast. So let's hope. Okay, it's done in about 28 seconds. So successfully. Okay, okay. So everyone is okay. Did you finish? Did you done the fan wrapping? So when I done it, I got this one. But I can do together with you. Okay, so let me try to do together with you. Just, it gives me everyone. Can I take with you? Can I take about 10 minutes? And we'll be back you after 10 minutes. Okay, everyone?
Okay.
Okay, thank you. Hello everyone, I'm back. Okay, so basically that's I have an appointment this morning, but I'm waiting until now. She just arrived, but and then it's okay now. So can we just start to from the beginning for the fan wrapping? Everyone's okay. So let me try to do together with you. That's okay. With Snafu, we have this one. So basically that is Snafu we have it here. Okay, maybe there's something wrong with the Snafu. So I just want to remove everything here. So we save here. So now again. What is this? What are you talking about? No, we don't want this one. No. So this one. Yes, 7 once, and then we try to. So I want to remove the Snafu again, and I want to just to run it again for everyone to follow the idea. So okay, the idea is we want to do fan wrapping in the graphic user interface. It will be more interesting. So I want to open the data again. So where we are in the data now flattening this one. So we have this one. So we have the bands, we go into the phase. Okay, this one better clean. And then we want to do fan wrapping. Just before I do that, doing that, is there anyone who already successfully to do fan wrapping? Yes or no?
No.
I
No.
can't. No.
No. Okay. So we do together. So you see my screen now, everyone?
Yes.
Okay. So we have the data. So we want to export it into the Snafu fan wrapping. Export to the Snafu. So where we are, we want to export into here. So I copy this one. So this is exactly the products I want to export. I copy this one. I put this Snafu. Okay. And the model is deformation. The methods is a minimum curve flow, and the number of rows is put one. And this one I put the run. Okay. Nothing difficult for you now. Okay. And I just want to track that everything fine with Snafu. So okay, it's here. So basically that is what they give us the coherence and the phase. All the Snafu need each of the coherence and the phase. And we have to remember this one. So basically that this is the one we want to do fan wrapping. So basically that's we're going to radar, we're going to interferometry, we're going to fan wrapping, we're going to Snafu unwrapping. Is okay, everyone?
Yes. Yes.
Okay, I click on that one, and this one is important. So this one should be the one they export. It should be in down here. So we're going to Snafu. We're going to this one. So we had to select the one here. This one. That is the one. That is the phase of the interferogram, and with the attention of Snafu. So we click on that one. Okay, everyone.
Yes.
Okay. Okay, so and then we're going to processing parameter. So basically that's it should be the one we where we want to upload exactly here. So copy it here, and we want to see changing. So it's okay, everyone. You follow?
Yes, it's running.
It's running. Okay, cool. It's running also for me. So 28 seconds, and I remember correctly. So 1, 2, 3, 4, 5, 6, 7, 8, 9. More than 28 seconds, I think so. Okay, 28 seconds exactly. So you done it, everyone?
It's still running for me.
Okay, still running. It means that it's working. So don't hurry. Okay. I'm waiting for everyone. Meantime, I just want to check everything's correct. My precision. Okay, it's done for number. So you want to lock? No. So we got to this one. This one. 7, 8, series. Go.
Okay, it's done for me.
Okay, it's done for you, everyone. And everyone. Before moving on, I just want to be sure that everyone can done it easily because I try to repeat it a couple of times. Okay, Thảo?
Yeah, mine is still running too.
Still running though. Okay. So I wait a little bit for everyone's done it and then we can moving on. So basically that we already export the data. We already done the fan wrapping. And then what we are going to do next is we try to bring it back to the snap. Why? Because when it's done it here, when it's done, basically that they generate the unwrapping phase here. So that is the unwrapping phase. And then how can we bring this back to the data? So basically that it's here. Basically that they already done it here. So let me check if it's when it's done, it's run to the output runners. So this one here. So you see here. So basically that so you see the phase here.
Yes, I have the same result.
Okay, so you see in the color manipulation, you can appreciate the value is changing from close to 0 until about 25. Okay, just to be sure, better image we import this color. So we select this one, and you can see it's more beautiful now. So we just want to be sure that from here to here, you see that the profile. So you see here, the profile we got is very smoothly. So the phase here, you see here, the phase, they have the absolute number now. Do you agree with me, everyone? So they don't have anything with the rough phase. So they don't, it look like that this one is done. But and then we need some information to put it something like longitude, latitude. So we have to handle with bring it back to the snap to this information to bring it back to this one. So basically, that's how can we do this one. So forgot to do that one. So basically that. So in my tutorial, if you cannot done it in the graphic user interface, you can done it easily in the terminal. So basically that's when you open the configuration file of Snafu and you got this command and you can run it easily in your terminal.
I tried to run it on the terminal. It doesn't recognize Snafu.
It doesn't recognize Snafu. Really?
But I managed to do it on the interface, so it's okay, I guess.
Okay, from my one, I gone to Snafu. Okay, I go to Snafu. Snafu is there. No? Okay. You see, Snafu is here. So if you want to see in my terminal, let me see in the window. Let me check it. Command. It's one command. So let me try to see, okay, the Snafu, it's working, it's there. So where is the terminal and where is Snafu? I guess in my computer is where it should be here. CD here. So it should be going to variable. Here I'm going to no, I'm going to wait here. I'm going to so we're going to auxiliary data. I want to where auxiliary data. No, we're going to Snafu. You see here. You see everyone. Snafu is here. So if you don't have it here, it should be Snafu. So here. So you see the Snafu is going to the bin. So yes, Snafu is here. So basically that is the for the window user, it should be here. And for the unit way Snafu. So for the liners, it should be just where you are installed. So basically, that's if you want to install where it should be there. Otherwise, they can understand in the folder of the user. So basically, that if we want here, we want to write okay Snafu, and it's okay. So basically, in the terminal, it's there. So how can I light this one? Power, no. Up. Let me try. Okay, that is Snafu in terminal. So if you want to run it, so basically where we are, if you want to suppose that if I want to run it in the terminal, no. Okay, if I want to go in terminal. So if I want to go in terminal, okay. Suppose that I just delete this one. No, it cannot delete this one because this one I can remove this one. Okay, just remove this one. Enough. Okay, so I'm going to show you how to do it in manual way. So basically, that I'm using this command in the configuration file. So basically, that is here. So we're going to Snafu like this one. So basically, if you don't have the Snafu, it will be like this one. So bin and Snafu, you got this one. So you got this one, and you run this one. So basically, I just want to track again here. So basically, that you have a Snafu configuration and the phase. So we run it here. So basically, that copy it here and run it here. So in the same thing, if we run in the terminal, so we're going to terminal. You see, it's running about 20. How many seconds? 28 seconds. I hope so. Let me try. Is this? So basically here in terminal is the same 27, 28 seconds. So whenever it's done, so we have the one here. We have this one. So basically that's the one we want to bring it back to the Snafu. So I open Snafu again. I want to snap again, sorry. So where we are, we should have this one. So we have this one. So until now, do you have the file wrapping available already, everyone?
For me, yes.
Everyone? It's okay for you for file wrapping?
My lab crashed, so everything has like.
Now, what about other people like Han? It's okay for you?
Just give up.
I'm just follow you because I also give up. I cannot open the image.
Why you give up? Why? It's so easy.
No, I cannot open the image. I waited for like 15 minutes and just now.
What have image you
Snap
cannot
is
open?
too much
What?
to us, like.
Right after the face removal, I cannot open the image, and then I close
Right
that
after
and
the frame.
reopen.
Okay, just wait a moment.
But I think that's not only my problem because we had also faced that problem too, but in later step, I think.
Oh, it's strange because it's quite straightforward. For even I face the same problem and I try to check for update and I restart the snap and it's will be gone. Did you check for the update also?
Yes, I tried. I tried any way I could, but no, I don't think that's the problem of the image. I think that's because of my laptop is not strong enough, I think, or something
No,
like
it's
that.
very small. It's very small. It counts how many megabytes of the image here. It's just about a few megabytes, so it's really small. So you see the processing it takes something like 1 or 2 seconds, or even 10 seconds.
Maybe because of the snap, it requires a large RAM, I think.
No, it's a require a large RAM when it needs for the processing image. The big image here is just very slow, very small image. So okay, don't worry. I am okay. So I just want to be sure that if you cannot follow, don't worry. You have the tutorial here. You can follow. You can done it later. Don't worry. So don't worry. Okay. Okay. So for those who already done for file wrapping, we try to bring the file wrapping back to the snap. So basically, we go to radar, we go to interferometric, we go to file wrapping. We try to bring it back here. So we the source of products, it should be the one here, and the written face here is where is. So the written, it should be where is it? It should be the one we done it here. So where is it? It should be in Snafu. And go into this one and go into this one. So you select the one we already done for the file wrapping. So you select this one. Okay. And then you go into do not save which to keep it there. So we're writing. So Snafu, but here with unwrapping. So it's unwrapping. And the one we want to store is where is it? It should be the one is here. So basically that. Okay, so so reading, okay, so we run it here. So it's very fast, if you can see here. So what do we have? We have, when it's done, you have the fan wrapping here. So you see here, he's in the rough phase and he is unwrapped phase. So this one is the interferogram and this one is in the phase. So and then what we're going to do is we try to transform this phase into the one we want to monitor in, that is the motion, that is the subsidence, that is the displacement. So we want to transform it to from the radar to the radar phase to the displacement. So we're going to interferometric, we're going to borders, we're going to fade to displacement, and we click on that one. It's okay for everyone?
I have a question.
It's okay. I just try to transform this phase information to the millimeter or into the value where we can appreciate the displacement. So we can go interferometric, go into borders, go into the phase to the displacement. It's okay. So basically, we take this phase, we multiply by 4 we divide by the wavelength. So we take this one and displacement. So okay, so nothing, because there's no this the processing parameter, because that's just a constant value. So we run it. And then we can see the displacement here. Okay, so let me check, is it correctly like this one from here to here? It should be like we already tried to do interpretation, it should be going down. So you see here, right? From here, so basically that's close to here is very stable. So people from the beginning from 0, and they go up something, they go down, they go down, they go down, something even about from 0 to 0, 1, 0 to 5 until something like 0 minus 0, 1, 2. So basically that's something like related to about 17 centimeter decrease. So you see that, everyone?
I have a small problem. Can you hear me?
Yes, I'm here.
I have a question. Do we have to do the import thing if we did the export without using the interface?
Oh, I'm not check it and delete this one. But usually we need it. We need it because otherwise they don't understand. I guess so. Or maybe you can try. I never try it because basically when you done the graphic user interface, you have the product that's open in for you in the product explorer. That's the output product, and
Yes.
in that case you have the phase, and you try to calculate it from the phase to the displacement directly. Can you do?
Yes.
Yeah.
I tried to do that, but it doesn't work.
It doesn't work, so you have to bring it back from using the function Snafu to Snafu import. Okay.
Okay.
Okay. So it's quite straightforward. So you radar, you go into interferometry, to go into Unwrapping, you go into import, and it's done. So you have displacement, and then what will you do? Okay. So basically that's what we try to do. We can appreciate that information to in other software like the Google Earth or something like that. So in a certain system GIS, so you're going to have to transform it into the Geocoding. You have to transform the azimuth direction and slant rain direction to the coordination system of a certain reference system in river, like the WGS 84 or something like that one. So basically we have to decode it by, how can we do this one? We do this one based on geometry. So based on this one, let me check is correct. Displacement, okay. So basically, okay. So just run this one. So basically that we transform, what we will learn to do if we try to transform this one in rain and azimuth coordination system, and we want to project it into a certain reference, like the datum of the WGS 84. So basically that's it, very classic coordinate system when we try to project it in a certain software. So we run it here. So it's running, and then what's going on? So we can see the information of this one here. So you change it here. So you see the displacement here is, well, what is this? The displacement here is very, it's just an image. So have say that is two-dimension array. So that is a matrix with a column and row information. It's corresponding to exactly the azimuth with exactly to slant rain direction. And then we're done for the Geocoding. So basically that we got this one. So this one is corresponding to exactly the longitude and latitude information. And we can even appreciate that information by just try to extract it into the Google Earth, something like this one. For this one, I not really like this color, so I want to change the color a little bit. So maybe I go to color manipulation, and I drag to certain this one. So maybe it's more beautiful. So I like it a lot. This one here. So okay.
Excuse me.
Go ahead, please.
May I ask why there is a flip from the when you do the step of terrain correction? Because as I observe, the image seem to be flipped from the left to the right. According to the previous one.
Because the data here is in rain and directions, and like this one in the image rain and azimuth direction, you see it very continuously like this one. But like okay, like I suppose that the sensor is here, and from here to here it is distant from the sensor and the data, and from if the sensor is going in here, the target is here. So basically the rain distance. So basically here it's just the distance from the sensor and the target, distance and the sensor and the target. And if we go into the river, the distance will basically depend on the topography. If the mountain or if the flat is totally different. Here we see it's capsite it's not continuously here because there is a mountain here. Why it's not continuously here? Because it's a mountain here. It's not continuously. It's not continuously here because it's mountain. But it's very continuously here because why? Because it's flat surface. So basically, that's the flat surface here, flat surface here, flat surface here is the mountain. That's why you see the image capsite a little bit. They have a shape of capsite very strange, but that is exactly due to the distance. So capsite, if we select one point here, so the distance from here to here is exactly the same. So because here the contribution of the elevation, they have to be restored a little bit to be sure that the distance is the same. that is the SAR image. So it means that we see very clean image here on the azimuth and range direction. Because why? Because that is the way the SAR image they store the range distance. It means that, for example, in azimuth, a certain azimuth here, everything in here they have the same direction, the same distance from here to the sensor. So let me check if there any information to appreciate that type point. You see here like slant right here. So I open this one. So you see here is the slant range type. So basically that here, let me track from here to here. If I draw a slant range type here from here, so it should be here even at a different row, different position, but the type is already also the same. So you can appreciate that information by using the profile you see here. The slant range type is almost constant here. So it means that the same distance. And from here to here, we can see the distance is changing. So basically that they're changing from let's delete all before moving on the next one. One. So you see here, the value is changing a little bit here, but very difficult to appreciate that because it's quite small. Because why? Because the type here they with respect to the second. So and in the velocity applied 1 second is a loss. That is why you see it changing very little, but it's changing with respect to if we go to the vertical like this one. So you got the idea. The idea with the image is from here to here in the same distance. So from with respect to the sensor, so that why it's very continuously like this one, very beautiful square matrix. If you go into the real world, they have a wrap like this one. So, and whenever we are happy with the image, like this one, if we are happy with the color, so basically you're happy. If we're happy, we try. If we're happy, we try to export it into a certain software like export the view to the Google Earth. So basically that I try to export into Google Earth. So where we are. So what should we be going to the M2 practical session? So okay, the replacement. I click on this, okay, and I go into this one, and that information is here. So I open the Google Earth software to appreciate the information that we have. And then you can see the value here, the units in the letter. So the blue one, so basically the blue one is the stable target. And then the one here is a very, but here no information. Because why? Because we forgot to show it. Oh, I need to show it once. So basically that's we subtract. I remove this one again. So why we forgot this one? Should be in tables, be basic, basic, math. Because straight up we forgot to to understand why this happened, why it's the hole here. So basically that's what happened. We try to understand. So PV here. So for us, yes. Do we have this one? Navigator. So we have very clear here why when we go into the transform it's gone. Very good. Very good problem. So basically that's all what's going on here. When we go to the displacement and we're going to transform it. So basically that we're going to transform again. And let's try to understand. Let's try to use other products for sample to be sure that everything correct. So basically, if we don't want this one, but we want to the unwrap phase. So we want to using the phase that we want to see the unwrap phase, but in the Geocoding direction. So we're going to this one. So we have this one in the Geocoding direction. So this one, so this one is okay. So we try to see it in the Google Earth again. So basically that's where we are. We are here, and we are here. So basically that is the phase. So we want to see the phase. Okay, so for the phase is no problem. For the displacement properly, there is some burst in the snap. That's why you see the hole here. That is this spread for me. So we will check it later when we have time. So you see, basically that's how you have the phase for the BAM city. And then you can see the information that we can appreciate by, for example, here you're going to subsidence, and here is upward, but there is a mass, so that's why we didn't see it. But basically, that's you have information for the interferogram. You know how to handle it, how to export it, how to decode it, and you don't how to do interpretation. You don't how to do remote topography. You don't how to improve the quality of the SAR data, the SAR interferometric phase data, and so on. So, but basically, that if you want to understand more, I can recommend you into my YouTube because you can see some tutorial inside for the top data. Basically, that's my video here. So this one is exactly the strip map mode. Basically, that's a very classic one, and a very easy one, a very small one also. So, but it's easy to understand. It's straightforward to understand the whole residue from the beginning. Do interferogram, do subtract the topography phase, do filtering to improve the quality of the data, and then try to do phase unwrapping. And then if you want to understand what's going on with the topmost, you can appreciate that. You can see my tutorial online also, because you can see the information online here. Like suppose if you want to see with the stand one, the topmost is a processing with Snap, you can see exactly the same thing here. So basically that okay, so basically that you will done exactly the same thing here. So basically that with the ground processing, it will be faster. So you have the interferogram, and you try to do phase unwrapping. So you do phase unwrapping by, so you export it, and you export it, and you do something like transform it to the displacement. So you see here. So basically that is the transform it to the displacement, and then you can appreciate how how the performance of the signal is, and then you can export it into the you can appreciate the information of the coherence just to try to mask something that's not really helpful, and you can export it into the Google Earth or something like that one. So you see, for example, you can export into the Google Earth like this one, that line, exactly the same thing, but I already show you with strip map. So if you want more information from the top, you can see in my in the YouTube, and then you can appreciate the information. And so basically that's nowadays, if you want to do some InSAR analysis, it's very easy for you because the data is available and it's free for everyone. So just go into the YouTube and and to see how it's working and how it's performance. And then I'm done for my job. Thank you for your attention, everyone.
Thank you.
Do you have any questions?
No.
No, it's okay.
It's okay.
It's okay. Okay, thank you a lot for joining me for 4 days together. So I know it's very busy for you because you are in the middle of everything to leaving for do an internship. I hope you. I wish you all the best. Goodbye, everyone.
Goodbye. Thank
Bye-bye.
you.
Wait.
Thank you. Goodbye.
May I ask about the final exam? Like, how would it be?
The final exam, how would it be? What does it mean, Thảo?
It will be exercises when where we need to calculate.
The final examination.
Yeah.
In this class, it's basically that you have three professor, Ben, Nicola, and me. For Ben, he already gave you the grant for the presentation, so you don't take any examination from his part. For Nicola and me, that you will take an examination about 120 minutes, but with the lecture. So basically, that you don't need to learn anything before. You can refer to, you can refer to your document, to your material during the examination. So you have 120 minutes to finish my part and Nicola part. So is it clear for everyone?
Do we have to do
Yes.
anything on Snap?
Do we have to do anything on
Snap or some other? I don't know. Do we have to do anything?
No. You don't need to do anything on Snap. I just show you how to how the practical is and how it's working. So you don't need to do anything on Snap. You will take your examination on paper. Only.
Okay. Thank you.
Okay. Thank you.
Thank you for the course.
Bye-bye.
Bye bye.
Bye.
See you in France.
Bye.
See you.